Hi everyone, thank you Mr. Cooper for introducing me. I'm happy to be part of this event and I really appreciate your interest in my work. Today I'd like to present you to show you 3 hypothetical but possible attacks on kernel data in the newest Windows 10 and a way to win this kernel mode battle. I think this topic is of critical importance for all security experts who are dealing with OS security. A few words about me. I've been exploring OS security for more than 10 years. I'm always curious about attacks on the OS kernel and how to prevent them. You can find my results in my blog. Today, I'm going to talk about 3 hypothetical attacks, 3 new attacks on kernel data. 2 of them show a way how to read and overwrite files opened without shared access. And another one shows how to elevate process privileges. All these attacks are based on patching memory data, and they do not trigger any Windows security mechanisms. I have discovered a technique that can prevent this kind of attacks. I'll show you my MemoryRanger, the tool which is designed to prevent attacks on kernel memory. One of the key features of updated MemoryRanger is a new data-only enclave. I've been developing my MemoryRanger for several years. Here are the corresponding research projects. You can follow the links below to read more about the MemoryRanger. Nowadays, kernel mode OS components and malware drivers share the same memory space with the rest of the OS kernel. All drivers can read and overwrite any part of kernel mode memory without any hardware restrictions. Therefore, modern operating systems are prone to kernel attacks. Look at the recent examples of kernel malware attacks. Robinhood ransomware that exploits a legal vulnerable driver to load a malware driver and disables security products. CryptoMiner that infected over 50,000 servers. It installs a malware driver to protect itself and abuses the computing resources for quite a long time. Gluteba malware that uses a set of kernel drivers to disable Windows security and finally hides its footprints. Our world is in danger. Who can save the world? Let's imagine that one researcher has invented a vivific elixir, an effective solution that can save the world. But here is the hacker attacker who wants to destroy the world. He is plotting to steal and modify the formula. It is very likely that he can succeed. That is why I have developed my MemoryRanger to prevent attacks on kernel data. My MemoryRanger guarantees that the secret data remains safe. Let's see how it works. It is obvious that the formula should be kept in secret. The researcher opens a file without shared access. No one can read and overwrite it. And here is a hacker attacker that wants to steal the formula and overwrite it. Usually, Windows guarantees an exclusive access to the open file and promises to block all other access attempts. But it is not quite so simple. The attacker can bypass this Windows barrier and gain access to the secret data. Today, I'll show you 2 possible attacks on this kind of files. Let's have a look at the details of file system routines in Windows kernel. Drivers use ZW-create file routine to create or open a file. Setting share access to 0 gives an exclusive access to the open file. ZW-write file and ZW-read file routines are used to write data to the file and read it. Let's have a look at what happens after the driver calls these routines. While calling ZW-create file, the control goes to the I/O manager, then to the object manager, then to the security reference monitor, which checks whether the access rights are valid. If access is granted, the control goes to the NTFS driver and then to the disk drivers. Security reference monitor is involved for each call of ZW create file. This subsystem checks the permissions and it can block unauthorized access. For example, it can return status sharing violation. Let's have a look at the details of read and write routines. Functions ZW-write file and ZW-read file use the same Windows subsystems, but they are skipping security reference monitor. OS uses file handle as a key to traverse through the following structures: kernel handle, object header with file object, NTFS data structures. For each read and write operations, OS gets through all these structures automatically without any security checks. The security reference monitor is not involved. We have two outcomes. ZW create file always performs access checking. ZW read file and ZW write file walk through the file structures without any security checks. This fact can be used by attackers in the following way. So, the secret file has been created in an exclusive mode and it is remaining open at the moment. The attacker can create a file, I named it a file hijacker. OS creates all the corresponding file structures automatically. Then, the attacker can modify the file structures in order to redirect the control flow to the secret file. As a result, all read and write access attempts to the file hijacker will be traversed to the secret file. So, the hacker can use three different hijacking techniques: handle hijacking, file object hijacking, hijacking of NTFS data structures. Today, I'll present you the details of two attacks: handle hijacking and hijacking of NTFS data structures. The link with the hijacking attack on file object was shown earlier. Let's move on to the handle hijacking. To understand the idea of handle hijacking, let me show you some details of kernel handle table. This table is used to store the mapping from the handles to the corresponding object structures. Windows kernel allocates a new entry for each created file. The entry includes object pointer bits. This field points to the object header structure. OS doesn't check the integrity of this field, and this fact causes the possibility of handle hijacking. Here we have a secret entry for the secret file and an entry for the file hijacker. The attacker can overwrite its object pointer bits using a value of object pointer bits from the secret entry. Now, all read and write access attempts from the attacker will be redirected to the secret file. The legal access will also be forwarded to the secret file. Let's see how it can happen. A researcher will open a secret file without shared access. The attacker will try to access the opened file twice. First, by calling ZW create file routine, and second, by using the proposed handle hijacking attack. Let's see how it can happen. Let's check the Windows version. We have the final one. The researcher is launching his app, which loads the driver. The researcher is opening a new file. He is writing the formula. He is reading the data to check it. The formula is saved in a secret file, but the file is still open. While the researcher is being proud of his job, for example, having a tea break, the attacker has a chance to steal the formula. The attacker is launching his app, which loads the driver. First, he tries to open the file using Windows function, and he fails. Windows blocks illegal access to the file. He is starting the hijacking attack, and he needs to have a file handle for the secret file. Let's assume that he's got this handle value. We can see that the attacker creates a file hijacker and patches the corresponding handle table. He's trying to read the secret file, and he succeeds. He has read the secret formula. And look, he's trying to modify the secret file. And then the researcher decides to check the formula again. The formula has been illegally modified, but let's wait for patchguard reaction, which is designed to prevent any illegal memory modifications. We've been waiting for 10 hours. It is quite a long time, and look, nothing has happened. The OS hasn't been crushed. The OS became infected, and the secret elixir is in danger. Okay, let's think about how to prevent this attack. We have to restrict write access to the object pointer bits without blocking write access to the other fields. Also, we cannot block read access to this memory area. My MemoryRanger has been updated to take into account this attack. Actually, MemoryRanger, it is a hypervisor-based project designed to block kernel mode attacks. The MemoryRanger can trap the loading of new drivers and move them to the isolated kernel enclaves. My MemoryRanger can allocate isolated enclaves in runtime with different memory access restrictions. The MemoryRanger allocates the default enclave for the OS and drivers loaded before. To prevent handle hijacking, my MemoryRanger moves two newly loaded drivers into separate enclaves. Next, it hooks ZWCreate file routine to locate the created file structures and restricts any illegal access to them. Red line indicate the illegal access attempts. This scheme helps to prevent handle hijacking attack by blocking illegal write access attempts. Let's see how it can happen. Let's check the Windows version. We've got the final one. The MemoryRanger hypervisor is loaded first. The researcher is launching his app, which loads the driver. The researcher is opening the file. He is writing the formula. He is reading the file to check its content. The formula is saved in the secret file, but the file is still open. While the researcher is being proud of his job and, for example, having a tea break, the attacker has a chance to steal the formula. An attacker is launching his app which loads a driver. First, he tries to open the secret file using Windows API function, and he fails. Windows kernel prevents an illegal access to the open files. He's starting the hijacking attack and he needs to have a file handle for the secret file. Let's assume that he's got this handle value. We can see that the attacker is failing to patch the handle table. He's trying to read the secret file, and he can read nothing. He's trying to overwrite the secret file. Then the researcher has finished his tea break and wants to check the formula. And the formula hasn't been changed. MemoryRanger prevents all illegal access attempts. Now, let's close both files to compare their content. We can see that the secret file contains only the secret formula and all attacker's input data is saved inside its file hijacker. Thanks to the MemoryRanger, the OS is protected. Okay, as a result, we have the following picture. The MemoryRanger restricts write access to the handle entry and prevents handle hijacking. Now, let me show you one more way, an absolutely new technique to access exclusively open files. It is NTFS data hijacking. Here we have file object which fields point to the control block structures. Let me call them NTFS data structures. These NTFS structures point to the other structures as well. OS doesn't check the integrity of the structures, which causes the possibility of hijacking NTFS structures. Here we have NTFS data structures for the secret file and for the file hijacker. The idea of attack is to overwrite the NTFS structures for the file hijacker using the data from the secret file. This can help to redirect read and write illegal access to the structures related to the secret file. The legal access will also be forwarded to the secret file. While I was checking this idea, I got the following blue screen of death. This bug check indicates that someone tried to release a resource he didn't own. Actually, this is true. I tried to use the resource which doesn't belong to me. How Windows OS has revealed this? The reason is here. Windows OS checks whether the current thread ID matches the value stored in the structure. If they are not the same, the OS calls kbugcheckx, which brings down the system. So, to bypass this check, malware driver needs to copy structures and patch the thread ID. Malware needs to repeat these two steps each time before reading and writing the secret file. Here is the scenario of the demo. The attacker will try to access the file twice using OS API function and using the hijacking NTFS structures. Let's see how it can happen. Let's check the Windows version. We've got the final one. The researcher is launching his app, which loads a driver. The researcher is opening the file. He is writing the formula. He is reading the data to check it. The formula is saved in the secret file, but the file is still open. While the researcher is being proud of his job, for example, having a tea break, the attacker has a chance to steal the formula. An attacker is launching his app, which loads a driver. First, he tries to open the secret file using Windows API function, and he fails. Windows kernel prevents an illegal access to open files. Then, he starts the hijacking attack on NTFS data structures, and he needs to have a file object for the secret file. Let's assume that he's got this value. We can see that the attacker creates a file hijacker and successfully patches the corresponding structures. He's trying to read the secret file. The secret formula has been stolen. He's trying to overwrite it. And then the researcher decides to check the formula. He sees that the formula has been illegally modified. What about patch guard reaction? Seven hours have passed and nothing has happened. The OS became infected and the formula is in danger. So, to prevent this attack, my MemoryRanger implements a similar technique. It runs drivers inside isolated enclaves. The MemoryRanger grants access to the NTFS structures that have been allocated by each driver. The MemoryRanger restricts access to the NTFS structures that have been created for other drivers. So, let's see how it can happen. MemoryRanger hypervisor is the first to be loaded. The researcher is launching his app, which loads a driver. The researcher is opening the file. He is writing the formula. He is reading the data to check it. The formula is saved in the secret file, but this file is still opened. While the researcher is being proud of his achievements and, for example, having a cup of tea, the attacker has a chance to steal the formula. The attacker is launching his app, which loads a driver. First, he is trying to open the secret file using API function, and he fails. Windows prevents all illegal access attempts. He is starting the hijacking attack, and he needs to have a file object for the secret file. Let's assume that he's got this value. We can see that now an attacker is failing to patch the NTFS data structures. He's trying to read the secret file. He reads nothing. He fails again. He's trying to overwrite the secret file. Then the researcher has finished his break and wants to check the formula. The formula hasn't been changed. MemoryRanger protects the file structures. Let's close both files to compare their content. We can see that the secret file contains only the secret formula and attacker's input is in the file hijacker. Thanks to the MemoryRanger, the OS is protected. So, as a result, we have the following picture. My MemoryRanger restricts read access to the NTFS data structures and prevents hijacking NTFS structures. That's all about attacks on file system, and now let's move on to the process privilege escalation attack. Let me briefly introduce this kind of attack. For each created process, OS kernel allocates several internal structures. One of them is eProcess structure, which includes the process information and pointers to other structures. One of the fields of eProcess structure points to the token structure. Information about process privileges is stored in the token structure. Malware authors invented various techniques to escalate process privileges. 10 years ago, attackers could easily add more privileges to the process by directly patching the token structure. Windows security experts prevent this attack by adding such fields as seed hash and restricted seed hash into the token structure. This guarantees the integrity of the token structure. Hackers made one step ahead and escalate process privileges by copying the address of token structure from a more privileged process. This technique is called token stealing or token swapping. Newest Windows Defender prevents this token swap attack by checking the integrity of these pointers. I will show you how attackers can escalate process privileges without triggering any security features. Now let me show you the details of the token structure. The token structure includes two parts, static part and a dynamic or variable part. The static part has a fixed size and has a link to the dynamic part. The dynamic part includes the process privileges, which are stored using a set of seed and attributes structures. Here we have two token structures for a high privilege system process and for the low privileged console application. The proposed token hijacking attack is to copy the whole token structures of the privileged process, including both parts, static and dynamic. Copying the static part is simple. To copy the dynamic part, attackers need to consider the interconnections between these structures. Let's see this idea. Here is the scenario of the demo with token hijacking. The attacker will start the CMD and his application, which allows the driver to escalate privileges. Then, the attacker will check that the privileges have been escalated by trying to disable Windows Defender. The commands to disable Windows Defender are borrowed from a banking Trojan called TrickBot. Let's have a look. Let's check the Windows version. We got the final one. The attacker is launching the CMD. We can see that CMD has users' privileges. The attacker is trying to disable Windows Defender using the commands from the Trojan. We can see a lot of error messages. They are the same and all of them mean that CMD doesn't have enough privileges to disable Windows Defender. The attacker is launching his app, which loads the driver. To start the token hijacking attack, he needs to know a CMD process ID. He is getting and copying the target process ID. We can see that the token structure has been patched. An attacker is checking the privileges again. We can see that the privileges have been elevated. the attacker is trying to disable Windows Defender again, and he copy-pastes the commands from the Trojan once more. He doesn't receive any error messages. We've just received a notification which confirms that Windows Defender has been disabled. The attacker can also disable even this notification. But let's see the patchguard reaction, which is designed to prevent illegal memory modifications. We've been waiting for 10 hours. It is quite a long time. Nothing has happened. The OS hasn't been crushed. It means that patchguard hasn't prevented this invasion. The OS became infected and our data is in danger. Okay. Let's think how to prevent token hijacking. The key feature of the token structure is that token structure has to be used only by Windows kernel, which have to access them. All other access attempts can and must be blocked. My idea is to create a special isolated enclave for sensitive system data. This enclave will include only token structures and Windows OS kernel core. All other drivers will be excluded from this enclave. The token structure will be excluded from all other enclaves. This idea helps to prevent illegal access to the token structures from all other drivers loaded before MemoryRanger and after it. Let's see how it works. Let's check the Windows version. We've got the final one. The attacker is launching his app, which loads a malware driver. Then we're launching the MemoryRanger to protect the OS. The attacker is launching the CMD. He's checking the privileges. CMD has user's privileges. The attacker is trying to disable Windows Defender again using the commands from the Trojan. CMD doesn't have enough privileges. To escalate process privileges, the attacker is getting and copying the process ID. Now, the attacker is running the token hijacking attack. We can see that this time the token structure cannot be patched. An attacker is checking the privileges again. We can see that CMD still has users privileges. Now, an attacker is trying to disable Windows Defender again. We can see a lot of error messages that confirm that CMD doesn't have enough privileges. Thanks to my MemoryRanger, the OS is protected. Okay, let's continue. As a result, we have the following picture. The MemoryRanger prevents patching the token structures by moving them to the special data-only enclave. Now, let's move on to the brief overview of my MemoryRanger and its main updates. The MemoryRanger is a tool designed to prevent attacks on the OS kernel with the help of kernel mode driver and a hardware-based hypervisor. The MemoryRanger registers a notification routine to intercept the loading of new drivers. the MemoryRanger allocates a separate enclave for each newly loaded driver. The MemoryRanger also intercepts the launching of new application. This helps to locate token structures and move them to the data-only enclave. The MemoryRanger can hook kernel API functions, for example, ZW create file, to locate the created internal file structures and restrict access to them. Hypervisor controls access to the kernel memory by restricting access and trapping EPT violations. The MemoryRanger provides a flexible memory access policy. The MemoryRanger can be easily updated to prevent new attacks on the OS kernel. Let me recap very briefly on what I have presented and what you learn. First of all, some Windows kernel data can be easily modified by attackers without triggering any security features. We have seen 2 hijacking attacks to access files opened without shared permissions and a new technique to elevate process privileges. I have presented an updated MemoryRanger which can prevent all these attacks. One of the new features includes a special data-only enclave to isolate sensitive data from all drivers. Eventually, thanks to the MemoryRanger, the world is saved. Thank you.
Okay, awesome. Thank you. I am looking at Slido for the questions, and currently nothing is popping up. That could just be because they are still in the mod queue, I'm being told. I will also mention you're getting very high marks for wearing a bow tie. I am still not showing any questions. I'm gonna refresh this one more time, because otherwise it would be just unfair to... Oh, here is one. Do the mitigations provided by MemoryRanger significantly affect system performance?
Oh, I got it. The first question relates to the performance issues and the performance degradation. How significantly performance has been degraded due to using security features. Actually, MemoryRanger has affordable performance degradation. All the details about the details of how I calculated performance degradation and how it can be improved, mentioned in my previous paper, which I mentioned early at the beginning. Actually, absolutely true. It caused performance degradation because at least we need to trap memory access. By the way, it is worth to mention that MemoryRanger is absolutely great solution to prevent access to the memory which doesn't have which access very rarely. For example, token structures, which do not very often accessed by the system. This is a great solution. The problem, the challenge, the hard issue is to prevent sensitive data, which has to be accessed in a protected way very often. This is the problem. But I think this is a global problem with restricting memory access. Thank you very much for your question. All the details are in my previous paper.
Okay, then we have another question, and that is there any way for Windows to completely mitigate the entire vulnerability class? And in your opinion, what is the best mitigation strategy?
This is our second question, relates to our global problem, how to prevent all vulnerabilities in our world. It's a complicated question. Point number one, if we fight with all vulnerabilities, all the security experts will be fired. Yeah, actually, this is a very complicated question. The thing is that operating system includes tons of codes, millions of codes, and as I understand, it's extremely complicated to reveal all the vulnerabilities. The idea which I mentioned in this presentation is just a first step to prevent the consequences of exploiting the vulnerabilities. So we cannot reveal all of them, but we can isolate the payload, inside isolated enclave, and this will prevent attackers, for example, from escalating process privileges. So it can run its own driver. Let's assume that attackers can run its own drivers, but they cannot patch sensitive kernel data. That's my point. My point is to isolate drivers from each other. If you, one point in this question I would like to mention that, in US Windows 10, Microsoft security experts introduce virtual security mode, which provides two modes, secure mode and normal mode. And they implement this feature using similar techniques, using EPT, using second level of address translation. And this idea, which I presented you, it's a more general solution. I implement several isolated enclaves. Windows implements just 2 enclaves. My idea is to implement several enclaves. For example, 3 enclave, 5, whatever. If we summarize your question, I think that reveal all vulnerabilities, it's impossible. It's a very tough question, but we can fight with the issue and prevent the consequences of code exploitation by isolating this code. This is my idea.
Okay, thank you. I'm going to quickly see if a new question has popped up. By the looks of it, it has not. So that was all the questions that we have for you today. Thank you very much for talk.